Okay, so today we're going to be going back over polynomial roots and inequalities. So just a couple of notes you're going to want to make sure you read through. Zeros of functions. If we have a zero of a function, then x equals a, and a is that zero. X equals a is a solution of that function when you set it equal to 0. X minus a is a factor of that function, and a is an x-intercept of that function. Some quadratic formulas over here, you definitely need to know that. Some special factoring. Guys, these formulas are not given to you on assessments. You need to be able to factor a sum of cubes and a difference of cubes and obviously a difference of squares. Steps for finding zeros, it goes back through the methods that we use, to find zeros, and we set the equation equal to 0. In other words, we set y equal to 0, and then we use things such as factoring, completing the square quadratic formula. To find a y-intercept, you just substitute 0 in for x. Fundamental theorem of algebra, it tells us that a polynomial function of degree n with real coefficients has exactly n complex roots. That is really important, folks. Notice it says complex zeros. So if you have a degree of 3, it may be that you have 3 real zeros, or you might have 1 real 0 and 2 imaginary zeros. Remember, if we have imaginary zeros, they always travel in pairs. So let's go ahead and get started. This first one, we start out with a quadratic. The degree is 2, so we should have 2 real zeros. But before we get going with that, let's go ahead and find the y-intercept. Because this is in standard form, we know when we substitute 0 for x, that we'd just be left with negative 18. It's always the constant term. So we know that the y-intercept is negative 18. To find those x-intercepts, we're going to set this equation equal to 0. So 0 equals 2x squared minus 9x minus 18. Now, notice that the directions say calculator inactive. So if all you're doing is going in your calculator and graphing this and trying to find the zeros, you're missing the boat on this. So since this is quadratic, you could use the quadratic formula. But again, if you do that, you're going to be doing a bunch of number crunching. So I always think it's easier to start out by factoring. See if you can factor it. So in this case, this is factorable. Our factors are, in the front, 2x and x. That's the only way we got 2x squared. And then you have to play with different factors of negative 18. And if we work through that, if we put 3 here and 6 here, that should work. 2x times 6x is 12x. 3x times x is 3x. We wanted to add a negative 9. The 12 would need to be negative. So therefore, we know that this is x minus 6 and 2x plus 3. Now, guys, at this point, we've been factoring. This is the 4th course you've been in, at least the 4th course you've been in that you've been factoring in. You're not going to see me sit there and take 5 minutes to factor. You've got to have your factoring spot on in this course. So if you still need to do it that long way, that's fine, but you better be able to do it fast. And I will go over that one time. So if you can't factor by guessing and checking, that's where you would do that AC product. You would say, okay, 2 times negative 18, that is negative 36. What two numbers multiply to negative 36 and add to that middle coefficient of negative 9? And that would be 3 and negative 12. You would then rewrite that trinomial's 4 terms. 2x squared plus 3x minus 12x minus 18. And then we use grouping. So what do the first 2 terms have in common? They have x. And then we'd be left with 2x plus 3. What do the next terms have in common? They have negative 6, and we're left with 2x plus 3. So what's the common group? 2x plus 3, we factor that out, and then we're left with our 2 GCFs, x minus 6. And remember, the order we write those factors in does not matter. All right, so from there, we set each factor equal to 0 and solve. So we have 2x plus 3 equals 0, and x minus 6 equals 0. So the first one, we'd subtract 3 from each side. 2x equals negative 3, and then divide by 2, so we get negative 3 halves. The second one, we'd add 6, and we get x equals 6. So our x-intercepts, or our zeros, they're the same thing, are at negative 3 halves and positive 6. And then our y-intercept, which we already jotted down above, is at negative 18. Notice it's a degree 2. We have 2 real roots. Now, at this point, if you want to check with your calculator, that's fine. Okay, so looking at the next one, again, it's in standard form. So we automatically know that the constant term is going to be the y-intercept. Okay, so we want to find those zeros. So we set this equation equal to, this function equal to 0. So we're going to say 0 equals 3x cubed minus 2x squared plus 12x minus 8. Recall, the reason why we do that is because f of x represents y. And anytime we want to find the x-intercepts, y is 0. Because this is 4 terms, the first thing we would look and say, is there anything that all 4 of these terms have in common? And they don't. So the next step is to factor by grouping. So right after that second term, I'm going to draw a line to separate these into 2 terms and 2 terms. So my first group here, what do they have in common? They have x squared. And then I'm left with 3x minus 2. If I come over here to my second group, and I look, what do they have in common? They have plus 4. And I'm left with 3x minus 2. So when I put those factors together, I have 3x minus 2 and x squared plus 4. Again, if you put x squared plus 4 and then 3x minus 2, it's the same thing. So then I check, because I still have a quadratic factor, could that be factored further? In this case, it cannot, because it has a plus right here. If it was a minus, it would have been a difference of squares, and we could have continued to factor in the linear factors. But because it's a plus, we need to go ahead and set these equal to 0 and work it out. And that's fine, guys. As long as you can get down to quadratic and linear factors, you will be able to work this out algebraically. So for this first one, we would add 2 to each side. We get 3x is equal to 2. Divide each side by 3, we get x is equal to 2/3. The second one, we would subtract 4 from each side. X squared equals negative 4. We would then take the square root of each side. Remember your square root property. When you are solving an equation, you take the square root of each side of an equation. You must remember that plus or minus. Square roots have 2 roots. They have the positive root and the negative root. And then because this is negative 4, it's going to be 2i. Don't forget that the square root of I, you might want to pop this up here somewhere. I'm sorry, not the square root of I. The square root of negative 1 is equal to I. So in this case, you have 3 roots, 1 real and 2 imaginary. And notice those imaginary roots are conjugates of each other. All right, let's look at the next one. It's another quadratic. So we can see that the y-intercept again is at negative 5 because it is in standard form. So we don't really need to substitute 0. We already know that. So to solve this, we're going to set it equal to 0. Now, most of you are like, that's not factorable because 5 is not a perfect square. But actually, you can factor it if you want. You just use that whole difference of squares system. If you have a term minus a term, you can always factor it using difference of squares by taking the square root of each term. The square root of x squared is x. The square root of 5 is the square root of 5. And then I make 1 positive, 1 negative. And if we can get it in that factored form, most of us can just know that, okay, well then when I set the first one equal to 0, I'm going to get negative square root of 5. And when I set the second one equal to 0, I'm going to get positive square root of 5. You also could have done it by, once you got to 0 equals x squared minus 5, I'm going to flip that around real quick. We would add 5 to each side, x squared equals 5. And then just like the last problem, we would use our square root property. So we'd take the square root of each side, and we get x is equal to plus or minus the square root of 5. So you can do this one by factoring or using the square root method. It does not matter to me, as long as you know how to do it correctly, and show your work. So for this one, our y-intercept is negative 5, and our zeros are at negative square root of 5 and positive square root of 5. And that makes sense if you think about this graphically. That's just your basic quadratic function shifted down 5 units. So if I drew a graph of this real quick, my vertex is at 0, negative 5. When I go out 1 from the vertex in each direction, we go up 1, out 2, up 4, out 3, up 9, which would be up here. And so you can kind of see if you graph it, and I know mine's not going to be beautiful, but you can see that those zeros are right here in between 2 and 3 and negative 2 and negative 3. And that's where the square root of 5 lies. It's a little bit bigger than 2. Okay, so I want you to do D and E on your own. Remember, start with things like if it's got, no matter how many terms, does it have a greatest common factor? If it does, pull it out, then see what you can do. Or does it have a difference of squares pattern? I want you to think about it and see what you can do. So go ahead and pause the video now. When you're finished, start the video back. Okay, so guys, for this first one on D, what you should first look for is a greatest common factor, and it doesn't have one. And the next thing we should look for, because it's that two terms, is it a difference of squares? And it is, because any variable raised to an even power is a perfect square. All you have to do is half that exponent to get its square root. And then 81 we know is a perfect square, and it's minus. So our factors are x squared plus 9 and x squared minus 9. Unfortunately, we cannot factor x squared plus 9 further with real numbers. Now, you can with imaginary numbers, but not real numbers. However, you can factor x squared minus 9 because it's a difference of squares. So that's where we get the x plus 3, x minus 3. Some students will go ahead when they get to these two quadratic factors right here and set them equal to 0. And if you want to do that and then use the square root method, that's fine. I'm just one of those people, I like to factor till I can't factor anymore. So for the x squared plus 9, you got to set it equal to 0, move it over, square root property, just like those last couple, and we get positive and negative 3i. And then the other ones, our real roots are negative 3 and positive 3. Notice that when I'm finished, this is a degree 4 polynomial, and I do have 4 complex roots. I have 2 imaginary and 2 real, and then the y-intercept's negative 81. All right, so this problem E is probably the easiest one we have. You've been doing ones like this since Math 1. It's got a greatest common factor, and when we factor out that x, we have a simple trinomial that factors to x minus 2 and x plus 4. So we set each factor equal to 0 and solve, and this one has 3 real zeros. The y-intercept is 0 because if you look at it, it is in standard form, and it doesn't have a constant term, so it's like it's saying plus 0 at the end. Also, the fact that one of your x-intercepts is 0, that makes it pass through the origin, so the y-intercept also has to be 0. All right, looking at this last one, here is one that's also a binomial. It does not have a greatest common factor. But when we look to see if it's a difference of squares, and we always want to do that, we always want to check for difference of squares first, we notice that that's not a difference of squares. So we then ask ourselves, is this a sum of cubes or a difference of cubes? And this is a difference of cubes. The first thing that I always do when I am factoring a difference of cubes is I always rewrite it as a perfect cube, minus or plus, if it was a plus one, a perfect cube, because that way you can then just apply your formula. So I'm going to rewrite our formula real quick. If I look up at my formulas, in case you don't remember these, this is the one for a difference. I wrote both of those formulas the same, but I'm following the signs along the bottom because it's minus. So pretty much using this formula, x is my a and 3 is my b. So when we go to factor this, our first factor is x minus 3. It's like you just drop those cubes out. And then it's going to be x squared, opposite sign, so plus x times 3, and x times 3 is 3x. And then it's always positive, and then I'd have 3 squared, since 3 is b, and 3 squared is 9. So we then set each factor equal to 0. We have x minus 3 equals 0, and x squared plus 3x plus 9 equals 0. And the reason why I'm setting this trinomial equal to 0, not trying to factor it, is I'm going to go ahead and tell you right now, if this is a difference of cubes or a sum of cubes, you are always going to have 1 real root and 2 imaginary roots. Your trinomial is not going to be factorable. And if you understand the graph, it's just a basic cubic function shifted down 27 units that only crosses the x-axis one time. So for the first one's pretty easy. X equals 3. We got it. Bam. The second one, though, we're going to either have to complete the square or do quadratic formula. And I have a feeling that most of y'all would probably pick the quadratic formula over completing the square. So we're going to say x equals the opposite of b, so that's negative 3, plus or minus the square root of b squared, so 3 squared is 9, minus 4 times a, which is 1, times c, which is 9, all over 2 times a, so that's 2 times 1. So we're going to clean that up. That's negative 3 plus or minus the square root. That's 9 minus 36, which is ultimately going to be negative 27, all over 2. So then we're going to break down negative 27, and I may just do this over to the side, just somewhere, kind of find some room. Okay, if I have the square root of negative 27, that is really saying the square root of negative 9 times 3, because we want to break it down to so we can see that perfect square factor. And we know that the square root of negative 9 is 3i, so that 3i is going to come out. And here, I'll write this over here so y'all can see it. So that's 3i, and we can't take the square root of 3, so it's going to stay inside. All over 2. And in this case, nothing reduces, so we are done. Just another little hint. Whenever you have a sum of cubes or a difference of cubes, when you find your imaginary roots, and they always should have I in them, you should always have 2 imaginary roots, it always ends up with the square root of 3 in it. So if you know that, that might help you when you're trying to simplify that radical. All right, so let's put our y-intercept and our zeros. Our y-intercept is negative 27, that constant term. Our zeros are 3. And then the next part, it's actually 2 different roots. It's fine with me if you write it as 1 as long as you understand that it's 2 different roots. One is negative 3 plus 3i square root of 3, and the other is negative 3 minus 3i square root of 3 over 2. Sorry, both are over 2. Okay, so how about solving polynomial inequalities? All right, so to solve a polynomial inequality, the first step is you've always got to set it equal to 0. And I say equal to, but obviously it'll be greater than or less than, or greater than or equal to, or less than or equal to. All right, the next step is you drop out whatever the inequality symbol is. As weird as that is, you have to find the zeros of the polynomial. So I'm going to leave that right there, but then I'm going to rewrite this. This is x cubed plus 2x squared minus 3x, and I'm going to set it equal to 0. And we're going to factor completely and find the real zeros. So we can see this has a greatest common factor of x. That leaves us with x squared plus 2x minus 3. And then that gives us x plus 3, x minus 1. So when we set each factor equal to 0 and we solve, we get that the zeros are at x equals 0, x equals negative 3, and x equals positive 1. So the first method is where we test values. Regardless of which method you're going to use, you always are going to draw a number line. So I'm going to come down here, I'm going to draw a number line. On my number line, I'm going to put the zeros of the polynomial. So important when you put your zeros on the number line that you put them in the correct order. If you don't, you're going to get the wrong answer. This number line pretty much represents our x-axis. All right, so what we're going to do is we are going to substitute values from each section. So before negative 3, between negative 3 and 0, between 0 and 1, and after 1, to see if they would actually satisfy the inequality. Would they make the inequality true? All right, so pretty much what you're doing is, as you substitute these numbers in, because when we set this equal to 0, it ended up coming out to be greater than or equal to 0. We're looking for, if we were to substitute values from each of these sections, would it make this inequality greater than 0 or equal to 0? If it does, then we shade that region. If it doesn't, we don't shade that region. Well, here's the kicker. We already found the zeros. So we know that every spot on this number line where we have a 0, we're going to put a closed hole because we already found where this function is equal to 0. That's why we're not going to substitute those numbers in. We're going to substitute the numbers between those to see whether it makes the function positive or negative. A quick way to do this so that you don't have to sit there and do a ton of number crunching is to use the factors and just to decide if that would make that factor positive or negative. So I'm going to give you an example. All right, so I'm going to pick a number before negative 3. Just any number, doesn't matter what it is. So I'm going to pick negative 4. So if I substitute that in there, and if I substitute negative 4 for x, it's negative. If I substitute negative 4 into x plus 3, negative 4 plus 3 is negative 1. So that's also negative. If I substitute negative 4 into x minus 1, negative 4 minus 1 is negative 5. It's also negative. Sorry, I didn't mean to write that one right there. All right. Negative times a negative times a negative is a negative because we have 3 negatives. So when I multiply these together, I get a negative. Is negative greater than or equal to 0? No, because it's not positive. So what that tells me is this is like false. I'm not going to shade this region. So do not shade less than 3. All right, so pick a number between negative 3 and 0. It doesn't matter what it is. So let's say it was negative 1. If we substitute negative 1 in for x, it's still negative. If we substitute negative 1 into x plus 3, it becomes positive. If we substitute negative 1 into x minus 1, it's negative 2, so it's negative. Well, negative times a positive times a negative, ultimately comes out to be positive. So that's what we want. We want it to be positive. So that's greater than or equal to 0. So that means we shade this region. And hopefully you're getting the idea. That's what happens. You just keep checking. And I'm trying to make this simple for you. You can, if you'd rather crunch it with numbers, you can. But if you can just figure out whether the sign would be positive or negative, that's all you're trying to do. Would that section be positive? Would that section be negative? So when I substitute here, this section was negative. That's not what I was looking for. This one's positive. This one ends up becoming to be negative, and this one comes out to be positive. And because we want to know when is this function greater than or equal to 0, we were looking for where it is positive. So our final answer would be from negative 3 to 0 in union with 1 to infinity. Now that's a really long, drawn-out way of doing this. So the better way is the graphing method. This is my favorite method. This is much quicker and a lot easier. All right, we do the same steps that we did before. You're going to set it equal to 0, and then you're actually going to really set it equal to 0 and find the zeros. You're then going to draw your number line, and you're going to put the zeros on the number line in the correct order. Negative 3, 0, and 1. All right, because we want to know when it was equal to 0, because it says greater than or equal to, we go ahead, just like we did last time, and put closed holes at these zeros. We know they are included in our solution. All right, then all you're going to do is use the degree and the leading coefficient to figure out the end behavior. Since this is an odd degree with a leading coefficient of 1, we know that the left arm's down and the right arm's up. We've also found where it crosses the x-axis. So I'm just going to draw a sketch of this graph. Left arm down, right arm up. I don't care about what it really looked like, how high the turning points went or low. I'm just trying to get a general idea of what the graph does. All right, then, because we were looking for where this function was greater than or equal to 0, we are looking for when the function went above the x-axis. So anytime it's above the x-axis, that's where we're going to shade. So we shade between negative 3 and 0, and then also from 1 to infinity. So our final answer here is the same as we got for the last one. All right, they would be the interval negative 3 to 0 in union with 1 to infinity. Okay, so let's do another one. We'll speed this up a little bit. I'll be really honest with you. Anytime I'm doing a polynomial inequality, I always do the graphical method because it's so easy to sketch a graph of a polynomial if you know the zeros. Now later on, we start getting into some harder inequalities like rational inequalities. That's where using those signs and kind of testing values is a little bit easier. But we'll get there when we get there. All right, so looking at this one, x squared minus x minus 2 is less than 0. Again, the first thing we do is set it equal to 0. It already is. Then what we want to do is we want to actually find the zeros. So I'm going to factor this. The factors are x plus 1 and x minus 2, and I want to know where it actually equals 0. So that would be at negative 1 and at positive 2. So then I'm going to come over here and draw a number line. I'm going to put my actual zeros on that number line. And remember, your number line actually is representing your x-axis. They're the x-intercepts. And I want to figure out when is this function actually less than 0. Well, folks, because I want to figure out when this function is less than 0, that is when it dips below the x-axis. Also notice in this one, it's not equal to 0. So the first thing I'm going to do is I'm going to come over here to this number line, and I'm going to put open holes at those zeros. This is a quadratic function. It graphs a parabola. It has a leading coefficient of 1, so it opens upward. So I'm going to draw a sketch of my parabola. And since we want to know when is this function less than 0, that would mean when it goes below the x-axis. So in this case, it would be in between these zeros, negative 1 and 2. So our final answer would be negative 1 to 2 with parentheses. And guys, the reason why that is true is because you got to think about that anytime you're below the x-axis, that's where y is negative. And the function represents y. Functional values are y values. Anytime you're above the x-axis, your functional values are positive. Anytime you're on the x-axis, your functional values are zeros. That's why we call them zeros. All right, so this next one we're also going to set equal to 0. So when we do that, we subtract the x cubed over, so I have 25x minus x cubed is greater than 0. If you would like to work on it from there, you can. Some people would like to divide that by -1 and make that x cubed positive, and that is fine if that's what you want to do. But if you do choose to do that, you better make sure you flip that inequality symbol. Remember, anytime you're working with an inequality, if you multiply or divide by a negative, you've got to flip the symbol. So pause the video and try this one now. So I chose to just leave it alone. So when I get to my roots, I get 0, -5, and 5. This is a cubic function. The leading coefficient is -1, because if I rewrote that, guys, that's -x cubed plus 25x. So that means that the left arm is up and the right arm is down. So I'm going to draw that. If you had multiplied through by -1 and flipped it, you might have a different graph, but we should get the same answer. And so I want to know, when is this function greater than 0? That's when it's above the x-axis. So that's over here to the left of -5 and then here between 0 and 5. So my final answer here would be from -infinity to -5, parenthesis, in union with 0 to 5. Parentheses on the whole thing. And I don't know what happened to my last answer. That one was -1 to 2. Must have disappeared somewhere. There we go. All right, so try the next two, see how you do, and then start the video back to make sure you got them correct. All right, so for C, when you move those terms to the opposite side, you get those 4 terms. You've got to factor by grouping. We factor all the way till we get 3 linear binomials, and we get our zeros are 3/2, -4, +4. The leading coefficient is +2. The degree is 3, so the left arm's down, right arm's up. We make sure we pass through those zeros. We want to know when it is less than or equal to 0, so that's where it's below the x-axis. So we shade anywhere that function went below the x-axis. And we get our answer. The last one, when you factor it, and you get your zeros, 2 of your zeros are real and 2 are not real. Well, guys, this is all about real numbers. Like what makes the function negative, what makes the function positive. So those imaginary roots don't matter. They're not going to affect it. So you just kind of throw them away. You only need the real zeros. So in this case, it's -4 and +4. We want to know when this function is greater than 0. So that's when it's above the x-axis. And so that's why we shaded on the outside of those roots, not including those roots because it wasn't equal to. And that concludes this lesson.